A laser is a beam of concentrated energy. Point a strong one at metal and it cuts through it. So here's something that shouldn't work. Point 6 lasers at a cloud of atoms, arranged just right, and the atoms get colder, not slightly colder. They drop to about a millionth of a degree above absolute zero, colder than anything in deep space. The key is what temperature actually means. Temperature isn't a substance and an object, it's just how fast the particles inside it are jittering. Hot means the atoms are flying around quickly. Cold means they've slowed down. So cooling something isn't about removing heat stuff, it's about slowing atoms down. And light can push. A photon carries a tiny amount of momentum, so when an atom absorbs one, it gets a nudge in the direction the light was traveling. A moment later, the atom spits the photon back out, but in a random direction. Over thousands of cycles, those random kickbacks average to nothing, while every absorbed push points the same way. The atom feels a steady force from light alone. But a push isn't cooling. A push just blows the atoms downstream. To cool, the light has to push against motion, whichever way an atom happens to be going. That requires the beam to somehow know which atoms are heading toward it, and remarkably, there's a trick that does exactly that. It's the Doppler effect, the same reason a siren sounds higher as it races toward you. An atom moving into a beam sees that light shifted to a higher frequency. An atom running away sees it shifted lower. So the atoms disagree about what color the laser is, based purely on how they're moving. So physicists detune the laser deliberately. They set it slightly below the color the atom likes to absorb. An atom sitting still sees the wrong color and ignores it. But an atom rushing toward the beam, Doppler shifts it up into exactly the right color and absorbs it, taking a push straight against its own motion. The faster it moves toward the light, the harder it gets braked. Now surround the cloud with 6 beams, up, down, left, right, front, back, all tuned the same way. Whichever direction an atom tries to move, it runs into a beam that becomes absorbable and shoves it back. Physicists call it optical molasses because the atoms behave as if they're wading through thick syrup made of light. There's a floor though. Every absorb and re-emit cycle also delivers one random recoil kick, so the atoms can never sit perfectly still. The same photons doing the braking keep jostling them. To go colder still, physicists switch tactics and let the hottest atoms escape, like blowing on soup, the ones carrying the most energy leave, and the average of what remains falls further. Push it that far and matter stops behaving like a crowd of particles at all. The atoms slow until their quantum waves overlap and merge into a single shared state, a Bose-Einstein condensate, thousands of atoms acting as one. That is where the world's best atomic clocks, quantum sensors, and many quantum computers start, not with heat and power, but with a beam of light used as a brake.